Hello and welcome to the segment 3 of first week sessions. So in this segment we will talk about the GPUs. So far we have seen the CPUs, the performance metrics, how to differentiate between the different workloads and especially the roofline model from CPU and GPU side. In this segment we will talk about basic GPU fundamentals to understand how the performance that we saw in the previous segment that is achieved. In addition to the GPU fundamentals, we will also talk about the modern AI accelerators. So there are so many accelerators or devices available nowadays to deploy the AI workloads that we want to accelerate in the modern applications. So after this session, you will be able to understand the SIMT execution model of GPUs. SIMT is single instruction multi-thread, and the CUDA cores that you will be looking at from the GPU side. So essentially you will be understanding the CUDA thread hierarchy, which happens to be threads, warps, blocks and grids. So these are the main components of CUDA thread that we will look into it. And also we talk about the different roles of other accelerators that are available in the market, not only the GPUs, like we have NVIDIA, AMD, Google, GraphCore, so many other GPUs or other versions of GPUs that are available from AMD, other versions of application specific integrated circuit based AI accelerators that are available from Google, GraphCore and so on and so forth. And from the GPU side, we will also look at the Tensor cores, which are very essential in the AI workloads. So we will see the spectrum of the AI accelerators that are available in the market, and also we will understand what exactly is appropriate for which workload. So what accelerators that we will go for if we want to deploy for, let's say, deep learning training, inference. There are many types of deep learning nowadays. You have the convolutional neural networks, you have the reinforcement learning based algorithms, you have the transformer based algorithms, you have diffusion models and so on and so forth, generative AI. There are plethora of AI models that we will work on, but what exactly the target accelerator or target device that we will go for different workloads, try to understand in this segment. So starting with the GPU architecture, the GPUs, the most significant or most important thing that you will hear in the GPUs is single instruction multiple threads, SIMT. So in the CPUs we have seen that CPUs extract the data level parallelism by using what? SIMD, right? So it's similar to that SIMD where single instruction is operated on multiple data. Here the single instruction is operated on multiple data but through different threads. So GPUs executes thousands of threads simultaneously in lockstep groups. So these groups are called warps. Okay. So here on the right side you are seeing one streaming multiprocessor, just a single segment block diagram that you are seeing from GPU NVIDIA H100 based or architecture based GPU. Okay, so this is just one single streaming multiprocessor that you are seeing. Okay, so in this streaming multiprocessor we have actually the warps or the main components which are running this single instruction multiple thread parallelly that here we are running, right? So GPU executes these threads, and warps, when we are talking about warps is collection of these threads. So 32 threads become one warp, that is the group, right? And these warp are getting executed in the same instruction on different data. Okay, so this is the SIMD at scale. You have 32 threads executing the same instruction on multiple data. Now you can imagine the SIMD that you have studied in the CPU side and the SIMD at scale that is operating in the GPU side. So we usually don't use if-else branches because it causes serialization, and essentially we avoid the if-else branching in the GPU kernel. So it's very data flow like kind of situation where we do not really care about the, or we do not see the kernels which have lots of control flow or if-else branches inside it. That is not good for the threads or parallel threads that is operating on single instruction and multiple data kind of situation. So these streaming multiprocessors that you are seeing here, here is this SM which is taken from H11100ASXM architecture, and this streaming multiprocessor each has 128 CUDA cores. Okay, so how these CUDA cores are operated or organized, that we will see in this streaming multiprocessor. Okay, so in the H100 you have such 132 streaming multiprocessors, right? So here you are seeing just one. Okay, so each streaming multiprocessor has these 4 execution units, as you can see, and these are basically nothing but warp schedulers. So each can have these 32 group of threads running in parallel at each clock cycle. Okay, and each SMs will have, so how many floating point units you are seeing? So AP32 32. So in each execution unit you have single precision 32 units, double precision 16 units, and such that you have 32 into 4 such cores that you have, that is basically the 128 CUDA cores that you have single precision. Okay, now each streaming multiprocessor also has this 16 integer 32 unit, which is basically integer 32 plus spatial functional unit plus load store unit. So essentially this unit is highly specialized for integer processing, integer operations, and spatial functional units are highly specialized for functions like sine, log, and different transcendental functions in mathematics. And also it has the load store units which are basically doing the memory operations, right? And you also have these tensor cores. Now tensor cores are the key ingredient for my AI algorithms or AI workloads. So that's why it's kind of mixed. So you have these CUDA cores. So when you hear CUDA cores and tensor cores, they are kind of separate. Okay, so CUDA cores are essentially these CUDA cores that you are seeing, 32 single precision and 16 double precision such cores are there. So these are specialized but not as specialized as CPUs. So these are very simple cores which can run very simple operations. And tensor cores on the other hand, they are highly specialized to do only matrix multiplication. So MAC operation, they can do small complete MAC operation, matrix multiplication and accumulation operation in one clock cycle. So they are highly specialized for the AI workloads that we are going to offload to the GPUs, right? So the streaming multiprocessors execute these 4 warps instructions simultaneously, and if they are waiting, once such warp is waiting for, let's say, data and they are not getting data, so this scheduler or dispatch unit will actually assign another warp and execute that. So that's how they will hide the latency that is wasted in the memory transfer and so on and so forth. So the CUDA, so essentially when you talk about the NVIDIA GPUs, the software stack that we are using as CUDA software stack, right? So CUDA framework that we have to use. So CUDA is essentially based on hierarchy model. So you have the thread, and thread couple of, or let's say multiple such threads based on which system target that you are targeting, which GPU that you are targeting. So that thread will make the warp. Here 32 is basically the collection of threads that is making these warps, and then they are making the blocks up to 1024 such warps, and then we have the grids, which are basically millions of such threads can be grouped together. So you can see that we have in the streaming multiprocessors, you have the register files as well, which is of size 256 kilobytes and organized as 65,536 into 32-bit registers. Okay, and we have this shared L1 cache, okay, among these warps, and you have also this L2 cache which is shared across the all streaming multiprocessors, okay, which is of size around 50 MB, and the cycle latency that you are seeing 30 cycle latency, and here you have the next stage of memory, which is everything is on chip that you have seen, which is the HBM3 memory that we talked about in the last class when we talked about the different hierarchy or different levels of the memory segment and their speed. And essentially this is where you are having this 3350 GB per second bandwidth in this. So you usually have 80 GB of RAM, which is basically this HBM3 memory that is shared across these multiprocessors as well. Okay, so this is your memory hierarchy, and this is your streaming multiprocessor, and inside that streaming multiprocessor you are executing this single instruction multiple threads as group, as warps, and basically they are dispatched by using warp scheduler or warp dispatcher unit. And then you have these CUDA cores, and then the special functional unit, integer units, and the tensor cores, as well as load store unit, which are basically. So this is the overall block diagram which you can keep in mind while doing the CUDA code running, because these sizes or the dimensions, the groups will make actually the number of threads that you want to run, you want to offload per streaming multiprocessor. So this is how this link between the system and the software will be having through this CUDA interface, right? So now we have to talk about the tensor cores, because tensor cores are the key or key system or key ingredient of the AI workloads that we are going to accelerate, right? So what is tensor core? Tensor core is a very specialized or highly specialized fixed function unit performing this operation, multiply and accumulate, which is matrix multiply and accumulate, D equal to A into B plus C, each are tiny matrices, okay, per cycle. So this entire operation can happen in one cycle for this GPUs using these specialized tensor cores. You have these tensor cores performing around 256 floating point 16 max per clock cycle basically, which is the fourth generation tensor cores used in H100 series of GPUs that you have seen in the previous slide, right? And what kind of peak performance that we can get, which is around 528 tensor cores into 256 operation per cycle, that is this floating point 16 operations into the clock speed is around, let's say, 1.98 gigahertz. So essentially you are getting around 270 teraflops performance, peak performance in FP16. Okay, so if you reduce the precision of the data type, you will get further improvement in the teraflops performance, and so on and so forth. So as I was saying, you can reduce or increase the data type's precision. So what are the supported precisions that we can have in the tensor cores? Let's see, we have floating point 64, FP64, we have TF32. So if we are using FP64, we will achieve this 67 teraflops, which is around 4 times less than the floating point 16, right? That's easily understandable. So usually high precision or double precision is used in scientific simulations because you need higher accuracy, but not usually used in deep learning training, because for AI workloads you do not need that much of precision in the data that we are using. Also you use TF32, which is of 19 bits. This is tensor floating point unit, which is TF32 data type and widely used for your training. So essentially if you are using FP32 in your code, which is single precision floating point unit or single precision floating point data, the hardware automatically actually drops to TF32. So essentially you will effectively use 19 bits instead of 32 bits, and that's how the performance will also go high. without even changing the code at all. Okay, so you have further precisions like BF 16, which is Brain Floating Point Unit 16, introduced by Google Brain initiative, and then you have Floating Point 16 also, where you get this maximum performance, peak performance of 1979 teraflops or T-flops performance. And this is standard for mixed precision training. Okay, so if you are using mixed precision training with this AP32 master weights, so this performance, peak performance will get. If we use further reduced precision, which is basically your AP8 or maybe INT8, so AP8 will give you around 4000 teraflops, emerging standard for LLM trainings, because your transformers are getting trained mostly using AP8. And if you want extreme throughput, which is more than 7 petaflops, so you can use INT4. Okay, so these are INT8 and INT4 are highly used for quantized inference. So training time we don't usually use this. We usually use for inference purposes the integer 8 or INT4 for quantized inference. So if you want, obviously you use quantized training, but that's the different way of doing training. So we were talking about this mixed precision because when we do the training, obviously in this at our disposal we have so many such data types, right? Floating point, full precision, double precision, AP64, TF32 which is 19 bits, AP32, BF16, AP16, AP8, INT4, INT8 and so on and so forth. So what exactly we should use and where should I use, we have given some idea, but we also can let the machine decide. So essentially we can use AMP library in the CUDA, which is mixed precision training, where weights are stored in AP32, which is the master copy of AP32 without changing the data type, single precision. But for forward pass and backward pass will happen via this tensor cores through automatic AP16 conversion, and essentially after the all steps are or gradients are computed, when we call this step, which is basically the gradient update, that time the master copy will get updated from this 16 bit of AP16 copies. So that happens both for AP16 as well as TF32. That is possible because you have this tensor core where you have all these data types supported. So based on these different like one example is torch.cuda.amp.autocast. So this enables automatic mixed precision within just one single line code, and it takes the data type and it sees in the forward pass, backward pass, the automatic transformation or conversion to this lower precision, and again return back the master copy with the full precision. So this is how the tensor cores are used in the software, but basically you need to know exactly what are the data types that are supported for this targeted system that you are using. Okay. So with this we'll just do a performance comparison between the H100 with its predecessor, which is the Ampere series, and you can see the floating point 64, which is around 20 teraflops. So here x-axis is representing different data types and y-axis having peak teraflops that you can achieve. Obviously you can have teraflops if you are doing the floating point operations, or you can have tops, which is tera operations, which are basically based on the integer operations that you can do. So 20 versus 67 in floating point 64, 156 versus around 1000. You can see, I mean 8x, 9x, 10x gain you get in the Hopper series of architecture compared to the previous generation of Ampere series. Okay, so beyond the NVIDIA GPUs, obviously it's widely used now. The NVIDIA is a giant in the AI workload domain. However, there are other players as well, and which are also rising, keep on rising, like let's say AMD. If we talk about AMD, obviously we have to talk about AMD MI300X, which was introduced in 2023, which is based on chiplet architecture, and it gets 1.307 petaflops in AP16 performance, which surpasses actually the performance of H100 architecture as well. Also in terms of VRAM available, you can see in Hopper series you have H100 80 GB, in place of 80 GB we have here 192 GB. So these are widely used for your LLM trainings and inferences nowadays. So best for LLM inference, because huge model you can fit entirely in the single GPU VRAM, virtual RAM memory here. Anyway, for the training you need to have to store all the different parameters that we will come to. It's not only the model parameters or the model weights, because you have to do the computation, gradient computation, updation, and what algorithm that you are using for gradient computation. Based on that also your parameters will go blow up. Okay, so usually the thumb rule is the inference, whether you can fit the entire, because at that time you are not doing any training, right? You do not have additional parameters into your model while doing the inference. So you can fit the entire huge model in this single GPU virtual RAM. Okay, you have Google TPUs. TPU V4 was introduced in 2021, and it's a custom ASIC. It's not having the general purpose CUDA cores as you have seen in the GPUs. So GPUs are good for your image processing, video processing, as well as the AI workloads. Here the TPUs are only for the matrix multiplication. So you have only tensor cores, and you have high T-flops like 275 T-flops in BF16, the brain floating point 16. I said that Google Brain has introduced this data type, so they support this. And obviously you have TPU pod V4, which has around 4096 chips interconnected via custom 3D Torus network, and you get high performance on this in this type of cores. So Google Cloud, through Google Cloud you can actually access these TPUs. You have Graph Core also, Graph Core IPU, which is highly customized for your graph neural networks, okay, which are highly sophisticated, because these are the neural networks which has lots of sparse computation. Okay, so graph cores are very good for those sparse computations, ideal for sparse and irregular workloads, so like GNNs, graph neural networks, symbolic AI, but this is very poor for matrix multiplication kind of scenarios where you have these, let's say, transformer models or the LLMs that you want to run, but these are highly specialized for graph neural networks only. Our cloud providers are also nowadays coming up with their own custom ASICs, which is like AWS is coming up with Trainium for your training jobs, and Inferentia. So this is another core that is used for AWS clouds. So it achieves around, so both of them are very good for your training. So usually they have this entire stack that you can use readily available for use in the AWS clouds. So usually for large language model trainings, this H100 series or MI300 series highly used. For cost efficient trainings we used Ampere series usually, and nowadays if you use low latency inferences you can use RTX series of NVIDIA GPUs or Inferentia, or these are used in clouds. So also Google Cloud uses this tensor cores for your different AI deployments. So now we have a global picture of different accelerators or devices available for your AI workloads nowadays, right? So VRAM that we talked about, which is virtual RAM, which is the binding constraint for your LLM training, because if you have, let's say, if we want to train the GPT-3 with 175 billions of parameters, so that means it comes around total of 350 GB of VRAM requirement. Okay, so but essentially we have single H100 has 80 GB, which needs around 5 GPUs to fit this entire model, right? So but the usage are usually not only the weights but also the gradients, optimizer states, as well as the activations. So essentially these four will accumulate simultaneously. So that's why I told that which optimizer or gradient optimizer that you are using for your training, right? Let's say Adam optimizer stores 3 copies per weight, so that means 3 times the weight size we need the storage data for, right? So for parameters, for the momentum calculation as well as the variance. Okay. So there are several mechanisms that people apply to reduce the memory reduction or memory requirements, like 0, 1, 0, 2, 0, 3, zero offload. These are different techniques. Zero redundancy optimizers. Microsoft DeepSeed uses this type of sharding, or let's say cutting out or chunking, or let's say dividing the optimizer states across different GPUs. Okay, so you have 0, 1 has 4 times memory reduction, 0, 2 has 8 times memory reduction, and so on and so forth. Okay, so how effectively you shard or you cut the chunks or the weights, and keep into different RAMs. Okay. So the practical VRAM budgeting formula is essentially your training memory bytes requirements is 16 times the model parameters for usually the ADAM optimizer we take into account. Your inference memory usually is 2 times the model parameters, because if you use floating point 16, or if you are using int 8, then you can go for 1 times model parameters. These are the requirements for high performance. Okay, so it's not only because you have to load the data again and again inside the RAM of the GPUs based on the requirements. Activation memory per layer proportional to batch size into sequence length and hidden dimension. So all these parameters we will again revisit when we will talk about the AI models basics and their application, or let's say the implementation for the different deployments. We'll come into these parameters, but these are different parameters or hyperparameters that are used inside your AI workload deployment. Okay, so these are different tools that you will be seeing in the upcoming classes. So in the summary, we talk about GPUs, but GPUs have also different ways to use. So there are different data types, different precisions that you can use. HBM3, which is basically the on-chip data memory, high bandwidth data memory that we use in the Hopper series, which has around this much of bandwidth, around 3 terabyte of bandwidth per second, is the key factor for defining the bandwidth advantage over the other architectures. You have AMD series, MI300 series, which offers you a very high VRAM HBM bandwidth as well as. So these are widely used in today's or modern LLM training and inferences. There are other accelerators also in market, like you have TPUs, IPUs, you have cloud ASICs for your training and inferences, and there are different optimization techniques for your sharding of data where to keep into different GPUs, because one single GPU may not fit the entire weights of the model. Okay, so with this we will conclude this segment. Thank you.